So starting with the first question, and let me also write winter 20 question paper 4.2. Question paper 4.2. Anyways, let's start. The first question is probably about the rate of the reaction, and so we're gonna start with it's saying that there's a reaction H2 and I2. A small amount of H2 is mixed with a large excess of I2 at a temperature of 400 kelvins, and the reaction is monitored. The graph obtained is shown. So, and he's saying suggest why a large excess of I2 is used in the experiment. So the very first thing, let me explain. There are two reactants. There's H2 and there is I2. That means the rate of the reaction depends on the concentration of these two reactants. It depends on the concentration of H2, and it also depends on the concentration of I2. What you don't know is how it depends on that. So you don't know what the orders are. So remember, there are three orders. There's 0, 1, and 1 and 2. So rate depends on the concentration of your reactants. You just don't know how it depends on that. If you have a zero order reaction, like if A is equal to 0, that basically means zero order. That means that the rate of the reaction is not dependent on the concentration of H2. Because if it has a power of 0, that means no matter what the concentration of H2 is, the rate would be constant. Anything to the power 0 is 1. So the value of the rate value is not going to change. Similarly, if A is equal to 1, if A is 1, that means rate is dependent on the concentration of the reactant, because if the power is 1, that means it's directly proportional. That means if you increase the concentration of H2, the rate of the reaction would also increase, and that means it's going to be directly proportional. And anyway, similarly, there is order 2, which means that the rate is very sensitive to the concentration of your reactant. If A is 2, if the order is 2, that means that the rate depends on the concentration of the reactant, and the power is 2. That means if you double concentration, the rate quadruples. So the rate of the reaction quadruples. So anyways, there are three orders. I mean, there can be more than that, but generally in CIE, there are three orders, 0, 1, and 2. You should know the meaning of each one. 0 means no matter what you do to the concentration of H2, the rate remains unaffected. 1, directly proportional, and 2 means that it's very sensitive. The rate would increase by a much bigger margin. You double concentration, the rate quadruples. You triple concentration, the rate becomes 9 times, right? Is this clear, Pasga? Saim, is this clear?
Yes, sir.
Yes, sir.
The first thing is, he's talking about why did he use, he doesn't even know why did he use a large excess of I2? Like, what's the purpose of using, how does that help if you use a large excess of I2? Anyone? Now, if you remember this now, whenever you use a large excess of something, then throughout the reaction, the concentration kind of becomes constant for I2. So one of the variables becomes, it stops changing, it becomes constant. Whenever you use a large excess of anything, so I mean, you can think of H2 and I2 reacting. For H2, you have 10 moles, and in the reaction for I2, you have, let's say, 10,000 moles. Now, whenever you use a large excess of something, if half of H2 reacts, the change in the moles of I2 is negligible. Like if half of the hydrogen molecules react, the moles they decrease from 10 to 5. That basically means 5 moles react. If 5 moles of H2 react, 5 moles of I2 will also react. So the moles of I2 will only decrease by 5. So from 10,000, it would become 9,995. So the change in the amount of I2 would be negligible. Bhaskar, this is reaction kinetics. Rate of reaction, basically, and orders. So remember this. Whenever you use a large excess of I2, the purpose of using a large excess is to keep one of the variables, because remember, rate depends on two variables. It depends on the concentration of H2. It also depends on the concentration of I2. But if you use a large excess, then the concentration of I2 is kind of negligible. There would be negligible change in the amount of I2 because you're using too much of it. If all of H2 reacts, like 10 moles react, the amount of I2 would only decrease by 10, and that change would be negligible. So the amount or the change in I2 would be negligible, and you can say that I2 is constant. Is the idea clear? And the purpose of doing that is because when you do an experiment, what you do is you find the relationship between two variables. So you want any other variable to be constant. Like rate has a lot of variables. A lot of variables are going to affect rate. Temperature, concentration, pressure. Lots of things are going to affect the rate of the reaction. So you want all the other variables to be constant. So if you're plotting a graph of H2, if you're trying to investigate how the rate of the reaction varies with H2, you want I2 to be constant. You want the other variables to be constant. And that is one way of keeping the other variables constant. So now if you change H2 and the rate changes, you know that it's changing because you're changing H2, because I2 is kind of constant. Is this idea clear? Clear? Is this clear? Yes or no?
Yes, thank you.
Okay. Bhaskar, is this clear? Omar? Saim? Saim, is this clear?
Yes, sir.
That's the next thing. So how do you figure out the order of the reaction? There are three ways. There are a couple of ways of finding the order of the reaction. One of them is the half-life method. So, I mean, this question, they're talking about the half-life. So they've plotted H2's concentration. As the reaction proceeds, the rate of the reaction slows down. So the descent or the steepness of the graph becomes slower and slower. It takes a longer time for the reaction to be completed. That's how most reactions happen. They're faster at the beginning, and then they start to slow down. If the rate had not depended on the concentration of H2, the graph would look something like this. It would have been a straight line. That the speed with which the reaction would have started with, it would have ended with the same speed. But since the rate is dependent on the concentration of H2, as the reaction proceeds and the concentration of H2 decreases, the rate of the reaction also decreases and the reaction slows down. It takes a longer time. And you measure the half-life. So for zero order, the graph is a straight line because the rate of the reaction is not going to slow down as the concentration of H2 decreases because it's not dependent on the rate. So zero order, the reaction would be, the line would be a straight line because the rate would be unaffected by the decreasing H2 concentration. This one is probably order one. Order one is directly proportional. Order one means that the rate is directly proportional. H2 decreases, the rate slows down. The way you figure that out is you measure the half-life. Half-life is the time it takes for the concentration to decrease by half, which in this case would be this. The second half-life would be the time required for the concentration to decrease by half again. And it's probably this line. The third half-life would be the time required for the concentration to decrease by half again. What you can see is that each half-life is kind of constant. So this is the first half-life. This is the time required for the second half-life. And this over here is the time that is required for the third half-life. So according to orders, for order 1, remember this, that the half-life would always be a constant. So half-life is constant, which is in this case. So that means it is order 1. If it had been order 2, the reaction would have slowed down by a much bigger margin. Like if the concentration decreases by half, if H2 gets used up, the rate of the reaction would decrease by 1/4. It would be a squared relationship. So in that case, the half-life would double. Every time the reaction would slow down and it would take a much longer time for the reaction to get completed. So half-life would double. And in the first one, the graph should have been a straight line. In the first one, the reaction would not have slowed down. It would just have continued in a straight line. And if you talk about half-life, in the first one, the half-life would be consistently halved. So that is the rule for half-life. To figure out order 1, the half-life should be constant, which it is in this case. So suggest why a large excess. So this one is order 1 because the reaction is slowing down proportionally. So the reaction, and they've already told you that the reaction is first order with respect to H2. So use data from the table to confirm the statement. So you only have to tell about the half-life. Tell them that the half-life is constant. Is this clear?
Yes, sir.
So 2 marks just for that. You measure the half-life, tell them every second half-life is constant. And you're going to draw lines to show that. So remember, that's one method. That's one method of figuring out the order of the reaction. First one, it's going to be, so just a quick revision. The first one, order 0. H2 decreases, the reaction does not slow down. So straight line going straight to the bottom, and the reaction speed will not slow down. Order 1, which is normally the case, like if you pour a fizzy drink in a glass, initially there's a lot of bubbles and then it slows down because the reactants get used up. So if H2 gets used up, the reaction slows down. So every time it takes a longer time. So the half-life is constant, directly proportional. Order 2, the reaction slows down too much. Every time the concentration of the reactant decreases, it takes a much longer time, and every time the half-life would double. So if the first one was 5 seconds, the next one would be 10 seconds. The third time, it's going to be an even slower reaction. The second method to figure out the order of the reaction is this table. What they will do is that they'll do a couple of experiments, or several experiments, and they'll keep on changing the concentration. They'll try and figure out what effect would that have on the rate of the reaction, which they're doing in this case. Now, 3 separate experiments were carried out, and they will try to figure out if you change the concentration of I2, what happens to the rate of the reaction, and so on. So use the data and the order of the reaction with respect to H2. So for H2, we've already calculated the order. So we know one of the variables already. I mean, we know that for H2, the order is 1. So one of them is already, it's already known, it's order 1. So he's saying use the data and the order of the reaction with respect to H2 given, deduce the order of the reaction with respect to I2, and explain your answer giving data in support of your explanation. So what you're going to do now is, what you can do it now is that you know the partial rate equation now. You know that rate depends on the concentration of H2 and you know that the order is 1, the power is known, that it's 1. What you don't know is the other one. It depends on the concentration of I2. Does it depend on that? You're not sure. So you don't know what the order is. So you don't know what B is. So the two variables that are missing. There's actually one variable that's missing, B. What I'm going to do is I'm going to plug in the data from each experiment into this rate equation, which I've partially figured out. I know this is one. I don't know what the other one is. So I'm going to plug in the data from the first experiment and I'm going to plug it into this equation. If I do that, the rate value for the first one is 2 times 10 power minus 17. So for the first one, it's 2 times 10 to the power minus 17. That's the rate in mole per dm cube per second. And the concentration of H2 given is 1 times 10 power minus 2. And I know the order for H2 is 1. And the concentration of I2 is also given 1 times 10 power minus 2. And I don't know what the power is. I don't know what the order is. So I have no idea what the relationship is. And then I'm going to plug in the data for the second reaction into the same equation. The data, experimental data is with us. It's so the second one is 2 times 10 power minus 15. So that's the rate. And that's proportional to, or what I can do is that's proportional to, what's the H2 concentration? That's 1 times 10 power minus 1. And that's power 1. And the other one is 1 times 10 power minus 1. And that is B, power B. So I've plugged in, I know this relationship partially. I know the order of the first one. I don't know what the order for the second one is. So I'm going to plug in the data from 2 experiments into this equation. And what I'm going to do is the data should be consistent. Like if there is a relationship that exists, then the data would be consistent. If you do an experiment with different concentrations, you're going to get a different rate, but the equations will be consistent. So what I'm going to do is I'm going to divide both of these. The proportionality would be replaced by an equal sign, and I'm going to solve this. So I've put in the data of 2 experiments into this relationship where I don't know what B is. And since they both belong to the same reaction, the data should be consistent. So the 2 equations are now divided together, and I'm going to try and find B. Now, the 2 gets cancelled out. 10 power minus 17. What is 10 power minus 17? And subtract that. So that I think would be 10 power minus 2. The first one. 10 power minus 2, and you add, so that's 10 power minus 1, I think, this one. And that is power 1. And the next one is 10 to the power, I think, minus 1, but it's got a power. It's got a power B. And I'm going to take this to the other side. So I'm going to divide that by 10 power minus 1. And what I'll be left with is just 10 power minus 1 on this side. So I'm just solving the math. And over here, I have 10 power minus 1. And the power is B. Now I've simplified this. And when I simplified this, I got this relationship at the end. So it's basically 1 over 10. I mean, 10 power minus 1 is 1 over 10. Is equal to 1 over 10 power B. Now, the only way only way this relationship is consistent is if B is equal to 1. I mean, if you want to solve this, B would be equal to 1. So that means the order over here in this rate equation would come out to be 1. So you just have to show them this working. That you know that the rate equation partially, you know that the first one is order 1. You don't know what B is. you plug in the data from two equations, two experiments, and then you divide the data or the two equations that you come up with, divide them, right side and left side, and then you try and solve for B. Is this clear? Saim, clear? Umar, is this clear? Bazga? Munir, is this clear?
Thank you. Yes, it is. Thank you.
Saim, clear?
Yes, sir.
So, and the reason we have to use, I'm going to explain this working as well. The reason we have to, because when you're given a table, there are actually two ways to solve this. I mean, if I open up any rate worksheet, then there are actually two ways to solve this. One of them is, I mean, if I just open, one way is to just look at the data. That's one way. You can by just looking at the data, you can kind of figure out the order of the reaction. I mean, some tables are really simple. Like if we see a table over here, there would be, just a second. Yep, this one. So if you have a table in front of you and by just comparing them, you don't have to do the math. What you can do is by just comparing, like if you compare experiments 1 and 2, if you compare them together, you would notice that you're not changing H2O2. So you keep one of the reactant constant. So one of the reactants is constant. The other reactant concentration increases by 3 times. And then you try to figure out by what factor. Sorry, it's not increasing by 3 times. It's increasing by, you're doubling the concentration of AuCl3. And you're not changing the concentration of the other reactant. So that means by looking at this, you can figure out the relationship between the rate and AuCl3 because one of the reactant has been kept constant. So the concentration doubles, and you would notice that this also doubles. So that means that's order 1, that you change the concentration, you doubled AuCl3, and the rate of the reaction also doubled. Like if you double this, you'll get this thing, 1.53. I mean, you can do that on your calculator. So it's increasing by a factor of 2. So that is basically order 1. AuCl3, it's order 1, directly proportional. You double concentration, the rate also doubles. Now this is easy because in the experiments, you kept one of the reactant concentration constant. The trouble comes in these questions, the one that we are doing. In this one, he's changing the concentration of each one of them every time. So you're not sure, is the rate getting affected by the change in concentration of I2? Like you can see in every experiment, the I2 concentration is changing. In every experiment, the concentration of H2 is also changing. So the trouble over here is you can't do this without doing math because the rate of the reaction is changing. You're not sure why it's changing. Is it changing because you're changing I2 or is it changing because you're changing H2? So which is why you would have to do all the math. Otherwise, you wouldn't be able to solve this question by just looking at it. The previous question was easy. I mean, this table was relatively easy. You don't have to do any math. This doubles, and you can see this doubles as well. Is that clear as well? Munir,
Yes, thank you. Yeah, it is. Thank you.
Okay, so he's now asking you to write the rate equation. So we figured out what B is. So that means it's order 1 with respect to H2, and it's also order 1 with respect to I2 as well. And to get rid of the proportionality, there's going to be a rate constant K. And you can find, use your rate equation and the data to experiment 1 to calculate the value of the rate constant. So now you know what A and B or the orders are. All you have to do now is, he's asking you to calculate A and K and find the units as well. So you can plug in the data from experiment 1. This is what he's asking for. So you can do the math yourself. It's just plug in the data. You know the concentration of H2, you know the concentration of I2, you know the rate of the reaction as well. So the only missing link would be your K. So you can find K. That's it. So just find K in your calculator by plugging in the data from experiment 1. And you can find the units as well. K would be, if I make K the subject of the equation, it's going to be rate divided by the concentration of H2 and the concentration of I2. So rate is what, mole per dm cube per second. I mean, they gave the units as well. You're going to use their units. Sometimes these things are given in pressure as well. So use the units that are provided over here. So rate is mole per dm cube per second, and concentration is mole per dm cube. So I'm not going to use mole per dm cube. I'm going to say mole per dm cube. I'm going to replace it with X. So it's mole per dm cube per second divided by mole per dm cube into mole per dm cube. So I'll first simplify this. The X will get cancelled out, and it will become X minus 1, S minus 1. So what was X? X was mole per dm cube. So it's basically, so the final result would be mole per dm cube to the power minus 1. So it's going to become mole minus 1 and dm 3 and S minus 1. So it's much easier to just use mole per dm cube, use X instead of mole per dm cube. It's much easier to simplify things. And that's your final unit. And you can find the value of, your value of K. So is this clear, the previous question? Is that clear?
Yes, thank you.
So then the next one is at 400 kelvins, the rate constant for the forward reaction is approximately 1000 times greater. So he's talking about the rate constant. So it's approximately 1000 times greater than the rate constant for the backward reaction. The overall orders of the forward and backward reactions are the same. So use this information to explain what will happen if equal concentration of HI, H2 and I2 are mixed at 400 kelvins. And you should comment on the relative initial rates of the forward and backward reactions and the position of the equilibrium reached. So we did kind of solve the first one, right? The first one we just did. I mean, we did all the math for the first one. It's H2 and I2. Those are my two reactants. We did that. And we also figured out that the rate depended on H2 and I2. We figured all of that. So for the forward reaction, we know for the forward reaction that rate depends on the concentration. So rate depends, like if I get rid of the proportionality, it's going to be equal to K times H2 concentration power 1 and I2 concentration power 1 as well. So use this information. So I'm just going to focus on the forward reaction. He's saying that the rate constant for the forward reaction is 1000 times greater than the rate constant for the backward reaction. So I'm just going to say, let's say the backward reaction, ignore the backward reaction at the moment, but I'm going to say that it's 1000 times greater. So I'm just going to call it 1000K. Because he's using the factor 1000, that he's saying that it's 1000 times greater. So I'm going to say that the rate constant is 1000K. And that's for the forward reaction. Now the backward is the reverse. Now he's saying that the overall order of the forward and backward reactions are the same. So in the backward reaction, there's only one reactant, that's it. In the backward reaction, there's only HI. So that means the rate of the reaction, the backward one, will be dependent on only HI. And he's saying that the overall orders are the same. So over here, it's going to be squared because you just have one reactant. Because the overall order in the first one was 2. This was power 1 and this was power 1. If you sum up the powers, the overall order of this first forward reaction was actually coming out to be 2. And he's saying that the backward reaction, they're going to be the same. So in the backward reaction, there's only one reactant, which is HI. So the overall order is going to come out to be 2, so it's going to be squared. So that's going to be okay. So this is what he means. That this is the rate equation for the forward reaction, and the value of k is 1000 times greater. So I called it 1000k. And this is the rate of equation for the backward reaction, and the value of k is 1000 times lesser. So he's saying use information to explain what will happen if equal concentration of HI, H2 and I2 are mixed. So this is what's going to happen. So if equal concentrations are mixed, let's take any concentration. Let's take 0.5, right? And H2 and I2 are also 0.5. So can you explain which one of the rate would be much higher if the equal concentrations of HI and H2 and I2 mixed together? So I'm plugging in the values of H2, I2 and HI. I'm just using 0.5 mole per dm cube. So which one, forward would be faster or backward would be faster initially? So anyone, any idea? Just a second. See, Bhaskar, that's right. Forward would be faster because the k value is 1000 times. Like if you solve this, it's going to be 1000 times bigger. Like it's going to be 0.5 squared into 1000k. Over here, it's going to be 0.5 squared into just k. So the backward rate would be 1000 times lesser. So he said that you should comment on the initial rate of the forward reaction. So initial rates, what we figured out is that the forward reaction would be forward rate would be 1000 times faster, 1000 times faster.
Still, I didn't get this. क्या मतलब?
Dekho, what he did was he said that there's a forward reaction happening, there's a backward reaction happening. So if you talk about the forward reaction, the rate depends on these two reactants, right? Is that clear?
Yes, sir.
So in the previous parts, he did calculate the order. Okay, H2 was 1 and I2 was 1. So we already know that. And he said that the forward, the value of the rate constant for the forward reaction is approximately 1000 times greater. So it's going to be 1000k, right? So you will get an equation which is rate is equal to 1000k because it's 1000 times greater, right? Into the concentration of H2 power 1 into the concentration of I2 power 1. Ibra, is that clear?
जी.
Okay, yeah.
And the backward one, he said that the orders are the same. He said that the overall orders of the forward and backward are the same. Now, in the backward reaction, you have one reactant, which is HI. So rate depends on the concentration of HI. But since the orders are the same, so this is going to be 2. Like the forward orders are 2, 1 for this, 1 for this. So the overall order would be 2. And he said that the backward orders would be the same as well. The overall order would be the same. So it has to be squared. Is that clear as well?
जी.
So the difference is that the forward K is 1000 times bigger than the backward K. And initially he said that what will happen if equal concentrations of HI, H2 and I2 are mixed together. So I just plugged in, let's say they're equal concentration. H2 is 0.5 mole per dm cube. This is 0.5 mole per dm cube. And HI is also 0.5 mole per dm cube. This is the rate of the forward reaction. This is the rate of the backward reaction. So over here, the rate would be 1000K multiplied by 0.5 multiplied by 0.5 or 0.5 squared. And the backward one would be just K multiplied by 0.5 squared. So both of them are being multiplied by 0.5 squared, but the forward rate would be 1000 times bigger than the backward rate. Is that clear?
जी, ठीक है.
You're getting the same expression except for this 1000 factor that's coming in. So
they mentioned that, yeah.
So that means, so he was very specific. You should comment on the relative initial rates. So forward rate is 1000 times faster than backward rate. As a next thing, what happens next? Where would the equilibrium shift now? The position of the equilibrium reached. Is it shifting forward or backward? I mean, the forward is faster, right?
Forward. Shifts to the right.
So it shifts to the right. Equilibrium is favoring the product. It's shifting to the forward reaction. Equilibrium favors forward reaction and shifts to the right? So you comment on that. And it's just a 1 mark question. So I mean, it's just a 1 mark question. So why did we bother so much? It shifts to the right. That's it. I mean, that would probably be it. That's about it. And the next, and I'll just comment on that further. So if it shifts to the right, like it's shifting, the forward is much faster. So the constant, now what will happen? Slowly the concentration of H2 and I2 will start to decrease, right? You started off with 0.5, but very, very quickly, the concentrations would decrease because, I mean, the initial rate is like really fast. It's 1000 times faster. So what will happen to the concentration of H2, I2? They would decrease very quickly. So the forward rate would slow down very quickly as well. Is that clear as well? Okay, I mean, you started off with equal concentration, so 0.5, everything was 0.5. But the forward reaction is very fast. So H2 and I2 will start getting converted to HI, right? So what will happen? The amount of HI will start to increase and the amount of H2 and I2 will start to decrease very, very quickly, right?
So the backward reaction will increase.
So this reaction, which is slow in the beginning, right? Initially, it's very slow, but it will start to speed up very quickly. Why? Because there's going to be a lot of HI formed by the forward reaction. Is that clear as well?
Yes.
And the forward reaction would start to slow down very quickly because the 0.5 mole per dm cube H2 and I2 will quickly start to decrease. So as the H2 and I2 get used up, the forward rate would slow down, and eventually they would become equal. But you're not going to comment on that because they were just talking about the initial rates and what will happen to the position of the equilibrium, like initially. But eventually they will reach equilibrium. Is that clear?
Yeah, thank you. That's clear.
So next is they're saying that at 700 kelvins, the rate constant for the forward reaction is approximately 50 times greater than the rate constant for the backward. So now so at a different temperature. Remember, the value of K is a constant. It only changes with temperature, just like equilibrium constant. Actually, this K is linked to equilibrium constant. So this value of K is now, what he's saying is that now it's 50K, just 50 times greater. So pretty much all the same thing would apply, but now it's just not, the forward reaction just is not going to be 50 times greater. So now he's saying use this information and the information to deduce the signs of the enthalpy change of the forward and backward reaction. Explain your answer. Now this one, he's talking about the sign of the enthalpy change. So what was the previous temperature? Did he mention the previous temperature? 400 kelvins, right?
Yeah.
And this is 700 kelvins. So is the forward being favored by a higher temperature, or is it slowing down?
It's slowing down.
So higher temperature, the value of K decreases. It's now just 50 times greater. So it's slowing down. So that means forward slows down, right? Like at 400 kelvins, the forward had a factor of 1000. It was 1000 times faster than the backward, right? But now the difference between the K values in the forward and backward is just 50 now. So that means the forward is like really slowing down now. So
they say, can we guess the forward reaction is exothermic?
now
at high temperature.
Now at high temperature, which reaction is favored?
Endothermic.
So what we can say is, if the forward slows down, what we can say, in other words, the backward is speeding up. I mean, relatively speaking, the backward is speeding up. So higher temperature favors, from the Shatler principle, we know endothermic, right? So that means the forward is not being favored, it's the backward that's being favored. So the endothermic is favored. So the backward is the one that's endothermic. The forward is the one that's exothermic because it's not being favored at higher temperatures. Higher temperatures favor endothermic reactions. Is that clear?
Yes. Negative.
So they linked this with Lee-Shatler principle, and we were able to figure out that higher temperatures favors endothermic. It's definitely not favoring the forward reaction, it's slowing down. So the forward must be the exothermic one. So deduce the sign of the enthalpy change for the forward, that's exothermic. And the backward one is going to be endothermic. And you're going to explain all of this. Higher temperature favors endothermic. Okay, is this all clear? This one.
Yes, sir.
And now this one is this one is about a dissociation constant. What is the dissociation constant? Dissociation constant is any acid is going to dissociate in this way. There's an acid. What does an acid do? It produces an H+1 ion and some other random ion next to it. That's how every acid dissociates. Like if I have ethanoic acid, it will dissociate in this order. It's going to release an H+1 and it's going to produce some random ion, which is CH3CO-1. And even diprotic acids will also dissociate. They will have two dissociation constants or three dissociation. Like if you have H2SO4, it will dissociate in steps. It will first release one H+1 and produce HSO4-1. And then that HSO4-1 is going to behave as an acid and it would release another H+1 ion and produce SO4-2 ion. So the general acid dissociation equation applies even to diprotic acids as well. Anyways, that's an equilibrium reaction. So how much does an acid dissociate depends on the equilibrium constant, products over reactants. So it's going to be, what's the K expression? It's H+1 concentration into A-1 concentration divided by the acid concentration, which is HA. So that's your acid dissociation equation. And you can further rewrite this as these two ions will have the same concentration. So you can rewrite this as H+1 squared. I mean, you don't need to write A-1 because if 2 moles of this are produced, 2 moles of A would also be produced. And HA is your acid. So it's your acid concentration. So K applies for a weak acid. Weak acids, they don't ionize fully, they reach an equilibrium. And that's the expression, H+1 sorry squared.
So if we do write A, to phir, I mean, do we get a mark or no?
Yeah, I think you'll get a mark for this. I mean, just to be on the safe side, write both of them.
Acha, sahi hai.
Okay. Now the next one is you're going to use this thing. He's saying that there's hydroxyl ammonium ion. I don't know what that is, but he's saying it's a weak acid, so it's probably going to dissociate in this way. I mean, I can. They're not asking for the equation, but it's probably going to dissociate in the same way. It's going to release an H+1 ion. But the K expression would be exactly the same. So he's asking you to calculate K. K would be H+1 squared divided by the acid concentration. So you just plug in the values that they've given you. What have they given you? They've given you the acid concentration, which is 1 × 10⁻³ . So that is given. So that is provided. They've given you the H+1 concentration as well because they gave you the pH. What is pH? It's 4.41. What does pH stand for? What does pH mean? Okay, what's the expression for pH? It's
minus log of hydrogen.
So it's the negative log of H+1 concentration, right? Base 10. And that value is 4.41. So if you take anti-log, this actually becomes 10⁻⁻⁴.41. Okay, so just remember very quickly that if you're given pH, then the H+1 concentration is going to be 10⁻⁴.41. I mean, you can use just, I mean, you can just take anti-log on your calculator, but it's basically 10 to the power minus 4.41. So that's your H+1 concentration, and that's going to be squared. So you can just plug in and you'll find the value of Ka. So remember this thing very quickly. pH is negative log of H+1 concentration. And that's 4.41. If you want to find H+1, that's going to be 10 power minus 4.41. Simply that. That's anti-log. And you'll find the value of K. And then they're asking you to find the value of pK. So once you have the value of K, P stands for negative log. So all you have to do is use your calculator. If you have the value of K, just take the negative log of K. I mean, there's a button on your calculator, which is log. Just press that, plug in the value of K that you calculated over here, put it in, and at the end of the day, just put a minus sign in front of it. Okay, is this clear?
P क्या होता
P stands for minus log. Like if it's pH, then that's minus log of H+1. If
है?
it's
अच्छा यार ठीक
if it's POH, that's minus log of the concentration of OH ions. If it's pK, that's minus log of K. And what was the reason of taking log? I mean, why didn't they use H+1 concentration? What was the story behind that? Why is log used in the first place? I mean, why don't they just like why do we measure pH? Why not just the concentration of H+1 ions? I mean, the reason behind that is that log, what it does is it expresses values in the powers of 10. So it's very good for making graphs. Like if I have a value of 10 and I've got a value which is let's say 100,000, and there's another value. Like if there's a large variation in values, it's very hard to plot a graph of these values. So if I have these three values, it's very hard to make a graph or to plot these values on the same piece of graph paper. 10,000, 10, and point. I mean, it's impossible to plot them on the same piece of graph paper. But if you take the log and you express it in powers of 10, this is 10 to the power minus 1, 2, 3, 4, 5, and 6. So it's 10 to the power minus 6. So if you take log, you're going to get minus 6. 10 is 10 to the power 1. And this would be how many? 5, 10 to the power 5. I think it's going to be 10 to the power 5. So if I express it in powers of 10, it's going to come out to be 5. So it's a lot easier to plot minus 6, 1, and 5 on the same piece of graph paper. That's why log is taken. Log is taken for values. So this is the reason why concentration of H+1 is not measured directly, because sometimes the H+1 concentration could be very low. Sometimes the H+1 concentration could be very high. So you can't plot a proper graph or plot it on a piece of graph paper and track the concentration of H+1. So it's better to use log, because log makes very good graphs. Is that clear why log is used?
Yes sir.
So here, let's continue this over the weekend. I mean, we'll try and do the same paper. Hopefully on Saturday then.
चलो okay sir, thank you. Love.
Okay, take care.